having me. I'm very happy to talk today. So yeah, this talk is going to be about understanding and communicating uncertainty in empirical research, which I think is a cross-domain issue, but it'll be focused on my domain of research mostly, but I think that lots of the things we say there could apply to other domains. So I'm currently working at Monash University, but I'm physically in Europe for a little bit. So that's why I'm on the same time zone as you, and it's still kind of light outside. But yeah, before I was in Linköping University, and I did my PhD in Paris. All of the things I'm going to talk about, there's a couple of references to works, to papers, it's all in there. So I put a small PDF with all the references, so you feel free to check it out. So my PhD was about 3D interaction and visualization. So how can we actually help scientists that work with 3D data sets to just like understand the data sets better? How can we provide them with tools that will help them analyze the data they have? That was the focus of my research as a PhD student. And also did some cool, weird projects that were not really linked to that while I was a PhD student, such as this one on visual sensory technologies. The idea there was to try and see if we could make shocking content less shocking, but just as informative, with the example of a surgery image here that we mimic with like a lasagna image. So we actually have a TED talk about this, TEDx talk, sorry. Feel free to check it out if you're interested. I think it's a pretty cool societal topic. And through my PhD, I got really interested in the use of statistics because I was a little bit upset about the way we relied on p-values all the time and the way they were reported. And that led me to get interested into transparency, open access, open science, the whole thing. Talking about open science quickly, I think I should mention that also is, of course, COVID-19. There's been lots and lots of research on COVID-19. And we actually decided with some people through Twitter, collaborations on Twitter, actually, people I'd never met before, to look at transparency state of like COVID-19 research and what has been done. And we published that paper that is fortunately open access, that is not very optimistic about what has been done when it comes to COVID-19, although some of the things would be pointing to like, oh yeah, all these COVID-19 papers are open access and all these things. We found things that were pretty worrying, such as papers that were accepted in a day or less, like reviewed and accepted in a day or less, which is a little bit weird. But anyways, let's get back to the topic. So yeah, in my field of research, which is human-computer interaction, often we sit people in front of computers and we ask them to perform a task, and we're interested in like seeing how good they are with accuracy, completion time, learnability, preferences for one technique or another, the workload that the techniques have, or how it impacts fatigue of the user. And often we'll gather data and try to conclude something along the lines of technique X is better than Y or faster than Y, or people tend to prefer X more than Y, whatever. But often it will also happen that actually we can't say any of these things and the findings are not that good. And so we decided with a co-author, Pierre, to look at whether or not we actually were very binary in the way we interpret our data, because there's more gray areas than just it works or it doesn't work. And that's the first paper that we submitted a couple of years ago. And so usually the process of the paper writing in my field is you conduct a study, you have data, then you analyze with statistical methods. Not always, it could be some qualitative, but let's focus here on statistical data. And you write the paper, reporting on what you found. But turns out what's going to happen when you run the statistical analysis is you either find sufficient evidence or insufficient evidence. And doing that is doing what we call dichotomous inferences. And these dichotomous inferences, if you look at p-values, they happen with the magic value of 0.05, right? If you're below it, you have significant results. If you're above it, then you have non-significant results. But they can also happen with confidence interval. Crossing the threshold that you set for yourself, such as 0 or 1 or whatever, would lead to significant or non-significant results. But what is quite problematic is that actually it's more than just making inferences. Having a paper that has enough evidence will lead to the paper being published, whereas if it doesn't, then it probably will not be published, or it'll be very hard to publish. And this is called the file drawer effect. It's quite famous. And it leads to the literature actually not representing correctly the state of our knowledge, right? Like, so in some cases, you might be able to publish some of these papers with negative results, but it will be very, very hard. And so the published literature doesn't really represent what we know. And if we think in terms of like medical research, which is very easy to represent for everyone, when we look for like specific evidence on the drug to know if it's efficient against specific disease. If we have like all of these very dichotomous inferences, then it's very hard to conclude if the study is run in multiple places and we have inconsistent findings, right? Like you don't really know what to conclude. But if the findings were reported correctly, so with the exact p-value, the exact confidence interval, so we can talk about effect size and all these things, that you might be able to conclude a little bit easier and you don't have inconsistencies anymore. Also, one issue we have with dichotomous inferences is that when we conclude that there's not enough evidence, if we look at the example of the drug, whether or not it's efficient against the disease, then we would just potentially exclude a drug wrongly, right? Like, because there's always uncertainty in data. So if we wrongly conclude for insufficient evidence, then we just exclude a potentially good drug. That's problematic, but not so much. But what if we change the question now to is that, does this drug have secondary effects on patients? Then we would just say that the drug is safe if we wrongly conclude there, and that could lead to problem. That actually happened a couple of years ago for a drug for an anti-inflammatory drug that just led to heart problems in patients. So yeah, this whole problem with statistics and dichotomous inferences, binary thinking has been reported a lot in the literature. There's lots of papers about this, including this one that's now quite famous. It was published in 2019, and it was co-signed by more than 800 scientists. And it was back then, before COVID, the paper that was the most ever shared on social media. So it was quite a nice paper. And I just thought, okay, how do we fare in HCI, right? HCI being human-computer interaction. How good are we with dichotomous inferences? And so are we subject to them in the papers that we have? What methods do we use to report results? And does it actually influence how dichotomous we are in the end? And like all of this literature on statistical analysis actually change what we've been doing in the field. And so that's why we decided to look at with Pierre. And we took all of this paper from the CHI conference, being the main conference for my field, and decided to just analyze them and what they report and how we conclude on results there. And so there was a total of more than 4,000 papers that we downloaded from the proceedings. We made text version of the papers through a Python script, and then we analyzed the text with Python again. So the first question we had was, what do we report at CHI, this conference again? And so we decided with a Python script to look for p-value inequalities. So we looked for exactly these strings, like p less than with or without space, p greater than with or without space, p equal to, and looking for confidence intervals as well. And so if a paper only reported p less than or p greater than, we concluded that this paper reported inequalities only. When the paper reported p equal to or p less than something, but something being smaller than 0.00 something, we concluded it was an exact p-value because we can consider that a very, very small p-value is probably an exact reporting. And if a paper reported both, then we just said that it was ambiguous. And so looking at what people report in the field, we saw that, well, half of the studies don't report p-values, and it seems to be like good with what has been published about this conference before, like because some of the studies are qualitative. We see that the number of exact p-value is probably rising through the years, and the number of p-value inequalities only is slowly decreasing. But most papers are actually a combination of these two. If we look at the number of papers reporting confidence intervals, where it's a pretty low rate, but it seems to be increasing slightly over the years. Now the question was, are we dichotomous in our result interpretation? And so to know that, we decided to look for the presence of significant or significantly in papers. But because significant and significantly can be used in context outside of statistical inferences, we decided to look for trigrams containing significant or significantly. And so we had a Python script looking for these trigrams, putting them in a Google spreadsheet. We had a lot of trigrams. I think the total is like, yeah, more than 10,000. And we decided to just remove all the ones that occurred less than 3 times to just try to reduce the number of trigrams we had. And so that brought us a list of like 1,250 trigrams that we then decided to code manually, Pierre and I. So the idea there was to try and code whether the trigram was about statistical inferences. So if you take this first example, no significant difference, it's probably statistical. But in the field of human-computer interaction, you have some people, for instance, talking about apps that you can have in like to talk with your friends or with your significant other. So in this case, significant others is probably not about statistical analysis. And then we just did a logical AND between our codings. So when we both said it was about statistical inferences, it was about it. One of us said it was not about statistical inferences, it was not. And if one of us had a doubt and said, well, it's probably not, then we decided that it was not. So we had a list of what we called the likely significance language trigrams. Then we run that list through the list of papers again with Python. And we could draw a list of papers containing this likely significance language. And so now we can answer our question, are we dichotomous in our results interpretation? And so you see here the rates of paper using either exactly statistically significant or using these trigrams or this likely use of significance language. And it's we had about half of the papers reporting p-values and about half of the papers actually using this significance language, which is not good probably. But the question was that, okay, can the reporting style we use actually influence how binary we are when we interpret results? And so you see here like a diagram of all papers at this conference. So the big circle is that. You see here all the papers that likely contain significance language. Here all the papers with p-value inequalities, and here all the papers with exact p-values. And so all of these papers now are all the papers reporting p-values. And this paper here, this group of papers here is papers reporting a little bit above. And so we see that most of the papers that we have found with p-values actually use some form of significance language that we derive from the trigrams. But now, if we look at grouping p-values all together, because we're not that interested apparently in like p equal p less than doesn't really change what's happening. But if we instead group them and have this time confidence intervals, we can see that it's actually, again, most papers reporting p-values use like a significance language. But when we look at confidence intervals, actually the number or the ratio of papers using confidence interval and not reporting with significance language their results is much higher than the number of papers with p-values not using significance language. So maybe there's something there that says that using confidence intervals could help in like reducing the use of significance language. So yeah, as I said, the vast majority of papers reporting inferential statistics do make dichotomous inferences apparently. We've seen some very modest improvements in reporting strategies over the years, but overall NHST-based dichotomous inferences have shown no sign of evolution since 2010, which was, by the way, the replication crisis in psychology-ish. There's of course lots of limitations to our analysis. One being that using Python to find text in PDFs, like when you convert PDF to text, there's lots of things that can be scrambled a little bit randomly. So in some cases, for instance, you wouldn't find this 95% bootstrap CI. It would just be scrambled all over the paper, and then you can't really match it to anything. There was also potentially false negatives and false positives in our trigram list that we coded manually. And so if there were, then whatever we did then with the Python script to tag papers as using significance language could also be influenced. For instance, if you imagine a paper that says the p-value is significant for speed, well, the trigram is significant for is correctly classified if we said that it was about statistical inferences. However, you can have this work is significant for our approach, and it's the same trigram is significant for, but if we said that it was about statistical result, then that would be incorrectly classified. So obviously, there's some errors that could have happened there as well. Another thing is that we only looked at significant, right? But there's lots of other ways in which you can be dichotomous, such as we found that there is no difference. We show that, we conclude that, we prove that. And we didn't try to look for any of these. We just looked at significantly because it was an automated approach. But I'll come back to that later. When we presented that paper in this conference, people asked us, hey, okay, but how can we actually describe our results without being too dichotomous? And there's no clear answer there. It's a little bit difficult, but we point on this website that I'll give in references that I have to papers from the field that actually have been using something, some alternatives to dichotomous reporting. They report confidence intervals, they use pre-registration and all these things. So people can actually get some inspiration from there to try and just read and maybe get inspired from it. But as I said, we had this problem that we only look for significantly, and we tried to solve that with the following paper. Definitely maybe. So the title is totally a reference to Oasis, because I think it's pretty cool to reference a rock band in a paper title, but also because definitely maybe actually plays a role. These two words are quite interesting. So let's imagine that we describe a drug trial result. With like, okay, we tested a drug on 20 participants and it reduced the viral load by 60%. So we would say the drug might have an effect on this virus because it's just 20 people, right? It's not really clear. Now, if we increase sample size, we might be able to change might to may, right? If we have 100 people, and if we have 1,000, then maybe we can say, well, the drug has an effect. Now, if we look at the viral load part, instead of just these sample size and the potential effect, we can maybe also change the way we talk about the effect. So if instead of 60, we have 51%, we might say, oh, well, the drug has a marginal effect on this virus. And again, we can imagine lots of different values that would somehow lead to different adjectives or words used with the effects we want to describe, right? And so all of these words, might, may, has, marginal, small, large, they actually play a role in describing the results we have. And they're quite interesting, and we can form lots of sentences to describe our results with lots of combinations there. But these words are really, really interesting. They are what the linguistic literature call hedges and boosters. And so I'm going to give a proper definition of these. Hedges are understood to be expressions that are used to turn down the force of a statement by making it fuzzier or more uncertain. This is from the linguistic literature. And the other way around, boosters are expressions that are used to increase the strength of a statement by making it appear more certain or sharper. And so, as I said before, we only look for significant significantly. There's lots of ways to be very certain in what you're saying beyond these two words. And the idea was to try and look at this in the same kind of literature that we did before, but going beyond this. And so we wanted to know how were edges and booster used at CHI, the same conference as before, when summarizing empirical results. So we again took the same conference, but this time we changed the number of papers that we had because we didn't want to analyze the full papers because they include also some manual analysis. So we only took 33 papers over 5 years. We sampled them randomly, of course. The whole process of what we've done is described in this figure. That's a little bit hectic, so I'm going to guide you through this. But we basically took, as I said, randomly selected 33 papers for each of these 5 years and prepared a coding spreadsheet with the paper's information first. Then we went to coding step 1. For each of the papers, we actually opened it in a PDF viewer, and we just checked if the paper reported a study or not. And if it reported a study, we looked at, okay, what kind of study is that? Does it report inferential statistics or just either descriptive statistics or just no statistics at all? And so we said that an inferential study is a paper that reports results using measures of statistical uncertainty, such as test statistics, p-values, interval estimates, et cetera, and they can be reported either numerically or graphically. But it doesn't have to be only that, right? If the paper reported just a little bit of that and then qualitative results, we still classify that as a paper with an inferential study. So then we had a list of papers and what kind of studies they reported, if any. We removed all the paper that didn't report on a study. So then we had 145 papers left, and we looked at the abstract. We decided to only look at the abstract because there was a lot of manual analysis. I'm going to get to that after. And we went through each sentence of the abstract and decided, right, does this sentence describe study results or not? And if it did, then we marked it. And so to do that, I just developed a small web application that just basically for each paper, where it was just like splitting the abstract into different sentences, and you could just click to mark it as like a result sentence, and then these results were exported. And once we had that, there was coding step 3, in which now for each highlighted sentence from before, we decided to look for hedges and boosters. And again, I created a small web interface to do that based on potential hedges and boosters from the linguistic literature. So it's very hard to find a complete list of hedges and boosters in the literature for linguistic research, but we used what we found was like quite common between all these studies from the past, and just highlighted all of these potential boosters and hedges in this web interface. So they were initially highlighted in gray, and you could just click on them to change, like red was a booster, blue was a hedge, and you could also underline a new word to make it a booster or a hedge, depending on what you wanted to make it. And why did we do that? Why didn't we just flag words as hedges and boosters? Because the context actually matters in how you perceive these words. So if I say it is possible that the drug has a clear effect on sleep, well, possible and clear are clearly hedge. One is a hedge and the other one is a booster. But now if I say participants said that they log when they went to bed as often as possible, in this case, possible is just used to describe the context or the instructions that the participant had. And so it's not really a hedge here, right? It doesn't work. And similarly, if I say participants complained that the instructions were not clear enough for this task, well, again, clear here is not a booster. So we don't want to have these two occurrences count in the account we have in the end. So that's what this interface allowed people to do, to just like take the context into account, classify words correctly. So how are Hedges and Booster used at Chi when summarizing empirical results with a question? And now we can look at the results we have. So pretty much here you see that, as we saw before, around 50% of papers report on inferential studies. This comes back to the results we had from the previous paper, right? And all the others are more like descriptive studies or papers with no study at all. About the sentences discussing results, not something very interesting here, but we just actually found that some papers actually had a study but didn't discuss the results at all in the abstract, which I think is quite funny. But it's not much to discuss here for you guys today. However, this is interesting. If we look at hedges and boosters in these sentences, so we have the mean number of hedges / boosters per thousands of words that we present here. And on the left part, you see like this breakdown between years. And we see that maybe for 2014, there was probably just a sampling error, because otherwise it seems that the use of hedges and boosters are just pretty consistent across the years and across paper types, right? Like inferential or descriptive studies. But yeah, 2014 is probably just a small sampling error. But now if we combine all of this, what we can actually see is that descriptive studies tend to use boosters less than inferential studies, which is quite interesting. And I'm going to come back to that later. Now we see the mean number of hedges and boosters per thousands of words, and we actually realize that lots of papers actually don't use any in their abstract, which is interesting again. I'm not trying to say that we should use them, but it's quite interesting to see that very often the number of papers not using them is pretty high. So maybe we should use them more, maybe not. I'm not sure, but actually it's something that was quite surprising to me as a finding. But yeah, now, as I said before, there were more studies, or inferential studies tended to use more boosters than descriptive studies. And so if we look at the top boosters in inferential studies, that's the one I highlighted on this image, booster or words such as showed, shows, or significant, significantly were like considered as potential boosters. Now we can wonder, okay, but show, maybe if I just use, like this study shows that X, Y, Z, maybe this is not really boosting too much. So is our analysis actually robust to removing these, for instance? That's something we decided to look at. So again, you see here just the difference in booster use in inferential studies at the top and descriptive studies at the bottom. And so these are the results we had before that I already presented. Now, if we remove the showed, shows from there, we still see that, well, this inferential studies seems to use them a little bit more than descriptive studies, but this difference is much smaller and it's more uncertainty now. If we remove just significantly or significant, effect's a little bit bigger, it's a little bit more certain, but not great. But if we remove both, then they're pretty much the same now, it seems. So maybe our results are explained by that, but I think in some cases using significant or show actually is quite strong. But that's something that if you were to code the same thing, you might disagree with. But yeah, there's lots of ways, I think, to show beyond significant or not significant that something is binary, and this is what we really wanted to look at there. And so we apparently showed that like this could be a concern, right? That we are very binary beyond the use of significant in our papers. Was the question we had at the end of this paper was, okay, is actually visualization or HCI, my fields of expertise, are these the domains that are the only ones concerned? Well, not really. It's something we looked at with other people on the threats of a replication crisis in empirical computer science, in which we look at all the potential threats to replication, or to robustness overall in the scientific process, by looking with the particular view from the empirical computer scientist. And when we submitted that paper saying it's lots of threats, we should just consider them, the reviews came back saying like, right, but okay, can you actually prove us that this is any threat beyond theoretical ones? And so what we did was we downloaded the 10 most cited papers of all the journals that start with transactions on from the ACM library, I think. So Association for Computing Machinery, so very computer science oriented. And you see here the number of papers that use a dichotomous peer reporting. And there's a lot of them in the top papers of these journals. So that, to us, proved that there was some potential threat there. Because we do know that dichotomous inferences actually are part of one of the issues of the replication crisis, actually. So dichotomous inferences or interpretations are overall omnipresent in empirical computer science. That's not so good. But maybe visual representation could help reduce dichotomous thinking. That was one of the ideas we had in this first paper, right? Like maybe confidence intervals could help if we visualize them, something like this. So we decided to investigate this a little bit more. And that's a paper that we recently published with colleagues from Linköping University, looking at visualization and how they could alleviate potentially dichotomous thinking. And so one first question that you have when you wonder if that could help is, how can I actually measure if people are dichotomous or make dichotomous inferences anyway? And well, again, coming back to p-values or confidence intervals, this is pretty much how we should interpret these, right? Like the p-value, if it's very small, we're very confident, and as the value grows, we just grow less and less confident. But this is not how we interpret them, right? Like we usually interpret them with like, oh, I'm super confident. And then we get to 0.05 and all of a sudden I'm not confident. And that is for the rest of the values beyond 0.5. And that sudden drop of confidence is called the cliff effect. And so it also happens with confidence intervals, right? Like usually when your CI is very far from the baseline, you're quite confident, you get closer to the baseline, all of a sudden you lose all confidence. And again, that's true for all the values. And we looked at the cliff effect, actually pretty old. It's been reported, I think it's 64 or something like this. So there's been studies on this. The problem is that often for these studies, the instructions given to participants are not very clear or not very well reported in the papers. The studies are pretty old. Some of them were even done on paper, so really old. And the classification of results, because you need to classify results into like profiles of certainty, was done manually. And this is very hard to replicate. And so we decided on the other end to just have like complete thorough reporting of our experimental design, to have 2 pre-registered studies on this, and to use a Bayesian analysis of our results so that we can actually help people replicate our findings if they want to. And so we tested in the first experiment 4 different conditions. The first one is just a p-value and confidence interval with text that you can find in almost all papers. The second one is just a classical confidence interval representation. The third one is what we call this gradient CI, in which we actually have the first part is the 95% confidence interval. And these parts here that are like shown with the gradient actually show all the other potential confidence intervals. So 96, 97, 98, et cetera, et cetera. And here we have a violin plot, which is also a classical representation, but it does pretty much the same thing as the gradient one, except in the gradient CI, this impression that like all values along the spectrum that is shown are just as likely. Whereas here we, come back to that. Here we show more of like, okay, this like the possibility of this value being the true value is maybe a little bit smaller the further you go out from the center, right? So we just thought, okay, if we make this, this line between the 95% confidence interval a little bit like fuzzier, of like where exactly it is, then people might eventually be less certain about what they're describing, which could be a good thing. And so we sent out an experiment to people with the following instructions. So a random sample of 50 adults from Sweden were prescribed a drug. And based on the information that we showed on the screen, we asked them how confident they were that the medication had a positive effect on body weight. And so we said increase in body weight. We wanted to stay away from, all the thing about losing weight all the time. And so they could just input their answer here on the slider, for which we didn't show an initial value to try to avoid biasing participants. And so we had different values, of course, that people could see. So you saw one here, and there's another one here, and we showed actually 8 different p-values or sets of p-values and results. So all of these here. I'm not going to read them out loud. And we'd send that around on Twitter, Facebook, LinkedIn, Reddit, and by email and Slack. And we got a total of 114 respondents, from which we had to remove 1 participant because they entered nonsensical demographics. And we tried to group participants into like research groups a little bit, like people from machine learning and statistics, whom you could expect they're a little bit better understanding statistics and not being too dichotomous, then people from our field, Viz/HCI, and people from more like natural science or other fields that were not represented in great enough numbers to be their own group. And so these are the results we obtained. So we mapped sorry about that. We mapped at the bottom the p-value that people saw, and on the left, we actually showed the confidence level that they had. And so if people were not like suffering from the cliff effect when looking at these, you should see almost a straight line, right? But turns out it's not the case at all. So what we see here is that confidence interval, which you can see in blue, there's really a big dip there of around 0.05 in the confidence that people have in the results. And this dip is actually bigger than with a textual p-value, which is interesting and actually contrary to past results on this. But for the other two, the gradient CI and the violence CI, we see that this dip is like slightly smaller, right? Like it's a little bit more leaning toward a straight line from end to from start to end. There's still a cliff effect, but it seems to be a little bit smaller, which could be promising. Then we also asked people what their favorite representations were. And it was no surprise that textual representations would not be well appreciated, but that, again, sorry about that, but that classic CI representation and violent CI, probably because people are used to them, were actually quite liked by people. Now, again, dichotomous inferences don't only happen when you have one confidence interval or p-value. It can also happen when you're comparing two confidence intervals, such as here, you're very confident, and all of a sudden, no more confidence because the confidence intervals overlap. And so we decided to run another experiment, always with 8 different p-values, but this time we removed the textual version and instead implemented this more like new gradient violent plot that was a little bit more discrete, like showing all the steps of the confidence interval a little bit better, and wondered if it could do something good. So we sent it around again. This time we got less respondents, 39 of them, 39 people only responded. And here are the results again. So quick reminder, we expect a straight line if there's no cliff effect. But we still see some form of cliff effect. So it's this time much smaller than the values we saw before. That's some potentially good news. Like if we map 2 different techniques, then it seems the cliff effect is less present. But it's still a little bit there. So we see also some things that seem nonsensical here, like for the continuous violent CI and for, which one is this one? The gradient CI, it seems that the confidence increases when the p-value increases. It's probably just an artifact due to our small sample size. Let's take it more as like a equal confidence across all of these values. But yeah, it seems that classic CI don't help much again, but maybe the violent CIs do. It's a little bit hard to conclude on these because of the small sample size and because of how tight everything is. But it could be that, yeah, violent CIs actually are kind of good. Maybe gradient CIs are actually good as well, but classical CIs we don't seem to do that well. Again, when it comes to preferences, we see here that the discrete violent CI was actually really liked by participants. Why is it a little bit unclear actually, but people seem to prefer it. So that's part of the results we have, although the discrete violent CI didn't seem to do as good as other things, but that's quite all right. But so yeah, to conclude on that, p-values seem to be quite cliffy overall. And visual representation could actually reduce this and seem to be preferred by participants, which is good news, I guess. So quick takeaways on this, so we can have some time for discussions. I wanted to find a quote about uncertainty. This is the only thing I found on Google. It was pretty lame, but I just thought I would put it there because it's kind of fun. But yeah, pretty much uncertainty is everywhere, especially in research. And I think we just have to acknowledge it and just know that, like, yeah, there's lots of things that we can't really categorize in a correct way and we can't be sure of. And that's quite all right, as long as we acknowledge it and say it clearly. The other thing is that words actually matter. You want to use the right words to describe the level of certainty or uncertainty you have in your results. This is very important. I don't think there's clear guidelines on this. I don't think there should be either, because language is cultural inherently. But we want to make sure to try and represent as closely as we can the certainty or uncertainty of our results. Last thing is, I think these things could actually help quite a lot. Maybe there's much more investigations to be done on that. I hope there will be more. I really think that visualization, which is one of my topic of research, can help. And I'd be super excited to see more people talk about this or try to use different things. It's, after all, science is an iterative process. We just started something there. We just hope that people pick it up and come up with new ideas, that would be extremely cool and exciting. These are the two sites that I mentioned about, like bad stats and dichotomous inferences. Feel free to look them up. They're also in the list of references that I put on my website, so you can find them there as well. One paper that I think is very cool as a pointer to finish is this paper from my colleague Pierre, in which they wanted to show in our domain the fact that, you know, the dense of the p-value and all these things. And so they pretended they were running an experiment in multiple parallel universes and actually put the name multiple time there as if they were doing the experiment in multiple universes. I think it's pretty cool and fun paper. Give it a read. I think it's pretty nice. That's it for me.
Thank you so much. Just gonna